Okay, thank you very much. It's always a pleasure to come back to Israel. I was here at Mahon Weizmann in 1980, and every trip to Israel is just a wonderful, wonderful time. So I'm going to talk about the Galton-Watson process, which was, as you can see, was quite controversial in terms of, here's a wonderful comment by Peter Jagers. And there they are, Galton and Watson in their glory. As Bailey explained, Galton came from an old family, a very distinguished family. And I'll just go quickly. We're going to use the Poisson distribution throughout, though possibly looks like the results can be done with other distributions. So we take the Poisson distribution, which is very convenient because of this property of how it splits, so a lot of the calculations become simpler. Oh, time for an advertisement. So actually, though I wrote this, I still haven't found the edition 4, so it's actually not available at fine bookstores nowhere, but it's supposed to be coming out any day. That's what I'm told, because you don't have a copy, do you? I don't either. Well, someday soon. Okay. So we're going to do the regular Galton-Watson process. The root has Poisson lambda children, and then the children have Poisson lambda children, and then their children have Poisson lambda children. Continues on possibly forever. And in studying it, it's convenient to use fictitious continuation. It's sort of a technical help. That is, you have an infinite sequence of IID Poissons, and then those determine how many children you have, but I call it fictitious continuation because even after the process stops, you can continue going. It's a very handy technical way I find to look at in studying the Galton-Watson process. All right. So let's look at a particular property. We can call this the old China property because they've just changed the rules. So the rule is, so here the property, so what I want to do is look at probabilities. In the random Galton-Watson process, what is the probability of various events? And this will be a function of the mean lambda. So we'll get some function of lambda. So as an example, consider the statement that some node has exactly one child with exactly one child. So to study this, we create a finite state space, green, yellow, and red. And green means that in that tree, starting with that node, there is a node which has exactly one child, which has exactly one child. And yellow means it's not green, but the node only has one child. So if you think of working up, yellow means you're halfway there. Okay? And now, what are the rules for determining the state of a node given the state of its children? Well, if it has any green children, then it's green. Because if it has a green child, that means in that subtree, there's a node which has one child, which has one child. So then the parent has a node in its subtree. So if it has any child that's green, then it's green. If it's not green, and if it has only one child, which is red, well, then it becomes yellow. So you're partway there. And if it has exactly one child that is yellow, so yellow means you have exactly one child, but you're not green. And so here are the rules. If you have exactly one, red is everything else. If you have exactly one child that's red, then you become yellow. And then if you have exactly one child that's yellow, but that means that yellow child had exactly one child, so then you become green. So these are the rules. And now you let X, Y, and Z be the probabilities of being in the three states, green, yellow, and red. So they're really just two variables because this is a probability distribution. And you get some equations for on X, Y, and Z because the Like the chance of being green is either you've got at least one green child, which is 1 minus e to the minus x lambda. Remember that if x is the probability of being green, then the number of green children is Poisson x lambda. That's where the Poisson really helps in the calculations. Or plus the probability that you have exactly one child and that child's yellow. So you get an equation for x, and similarly you get an equation for y. They're really only two variables because these are distributions. And when you solve this, you get a unique solution. And there's the solution. Actually, there's the solution for 1 minus the property. So this is actually the graph of the property that you have. There's no node that has exactly one child that has exactly one child. Okay, and you get, so it's given by this implicit function, and it's a C infinity, it's an algebraic function, and everything's right with the world. Okay, now let's go to the classic case that Galton and Watson studied, because they were interested in whether what they considered the good people, the aristocratic families, were going to continue forever or not. So they were interested in whether or not the tree would be infinite or not. And so this is classic work that you can find in any book on the Poisson, on the Galton-Watson process. There are two states, green and red. Green if there is an infinite tree coming down from the point, and red if not. And then if you have any green child, you're green, and otherwise you're red. So there's only one variable, the probability that you're green, and you get the famous equation. There it is, the famous equation that x equals 1 minus e to the minus x lambda. But there are two solutions. And this is well known for people in the field. There's the correct solution. This is for lambda greater than 1. For lambda greater than 1, there are two solutions. So and there they are. For lambda less than 1, the probability of being infinite is 0. The solution to the equation is 0. But for lambda greater than 1, there are two solutions, x, the actual answer, which is this curve, and 0, which is the wrong answer. But still, it's the correct answer to this system of equations. Now, oftentimes this is considered just some kind of anomaly or so, but this will be the center of this talk, is why do we sometimes have two solutions and sometimes have one solution? So let's take an even more extreme case. Let's imagine that Shas wins the next election, and they decide, that for the strength of Israel, they're going to introduce a rule that if you have less than 2 children, then you are removed from the state. So you might think that Noga is okay, because we saw Natalie, and we saw Narkish, and we saw Neely, but not so fast, because there's a further rule that you see after your children are killed off. If you don't have 2 children then you will still be killed off. So Neely's doing her job, but suppose that Narkish and Natalie each only have 1 child. Well, then they will be killed off, and then poor Noga. Well, it's a bleak view, but I'm thinking of Shash in control of this country is always kind of bleak. So, okay, that's enough politics. That's enough politics for now. Nurit is working on it. I hope Narkis and Natalie too. Okay, so and in mathematical terms, we're asking whether there's an infinite binary tree, starting from the root. Okay, and that's the property we want to look at. And now we just say 2 states, green and red, and you're green if, it's hard to read, You're green if you have at least 2 green children, and otherwise you're red, okay? And that defines the states, and then you're green if you have the infinite binary tree. And you have the infinite binary tree if and only if 2 of your children, 2 or more of your children, have the infinite binary tree under them. And so you get this, and you get this nice equality. The equation looks kind of nice, and it's always good to, it's a good one to give to your first-year students, which means it's a good one to try yourself. It's a lot of fun to work on this equation, and you get all sorts of strange stuff going on. Calculus can be fun. And the end result is that actually, for lambda up to some critical point, around 3.4, the probability of having the complete binary, if you look at the equation, it only has the solution 0. So the probability of having the complete binary tree is 0. But after you reach this critical point at 3.4, the equation actually has 3 solutions. You've got, 0 is still a solution, red is another solution, and gray is another solution, and the actual correct answer is the gray curve. In fact, one of the things we're not sure of is there any interpretation of the red answer? You know, we talked about that at one point, but ill-formed question. So here we have one with 3 different solutions. Okay, so I want to look at properties, and I want to look at them from the point of view of logic, and I want to consider statements in the first-order theory of logic, which means what we have the normal Boolean connectives, and we have quantification, but only over vertices. We can't use, as Saharan said, you can't use the word set in your sentence. You can say there exists a vertex V, and there exists a vertex W, and you can use the word parent, and you can use the word root. And the sentences have to be finite. So if you want to say there exists a vertex V, and there exists a vertex W, and a vertex X, and V is the parent of W, and W is the parent of X, you can say that. But you can't say that there exists a set of elements that have a certain property. So this is called the first-order theory for rooted graphs, and there are some examples. And a key thing when you're looking at first order is what's called quantifier depth, which is the degree of nesting of the quantifiers. Not the number of quantifiers, but if you have quantifiers inside of quantifiers inside of quantifiers inside of quantifiers, that's quantifier depth 4. And that's the thing that we'll use. And basically we'll be thinking of, suppose the quantifier depth is fixed, then what can you say about the statements?
Okay. So you say in this example the depth is 4?
What?
The example you...
Yeah. For all, there exists X, there exists Y, there exists Z for all W. Each one is inside the other. Yeah, but it's not 5 because the for all V is not inside the for all W. Notice the brackets. So it's not the number of quantifiers, it's how many are inside each. And this can be formally defined, but and this is a standard definition. Okay. So one of the big theorems is that if you call this is rooted trees, it could be almost anything. If you call 2 rooted trees the same, if they agree on all the statements up to quantifier depth k, that there are only a finite number of equivalence classes, even though you think you might stretch out the sentences. But up to tautology, there are only a finite number of sentences of quantifier depth k. And this is not easy to prove. I like to prove it using the Ehrenfreud game, but I'll just state it. And just to point out that the number of equivalence classes actually goes like the Tower function of k, so it's not quite clear. Now, if we're looking at quantifier depth k statements, It turns out that in the first order world there's a locality. So you look at the local balls, and you can give them radius 4 to the k, some function of k. And if you look at the balls of radius 4 to the k around the various points, if you have at least one ball of each class, actually if you have at least k ball, there's something about the disjointness of the balls too. If you have at least one ball of each class, then the Ehrenfreud value of the tree is determined, except for what happens near the root. Because near the root, you can't distinguish between the root having 2 children or 1 child. The root's a designated point. But saying that once you have all these local structures, then the Ehrenfreud value, so the Ehrenfreud value is the equivalence class. What is the truth value for all first order statements up to quantifier depth k? That's what the Ehrenfreud value is. And there are only a finite number of Ehrenfreud values. And the theorem, this classic theorem, is that if you have all the local neighborhoods, there's of all the different, and there are only a finite number of types of local neighborhoods, then the Ehrenfreud value is determined by what happens near the root. And putting that, actually, one can create a single tree, a Christmas tree. If for each thing you need, if you just glue them together, you get a single tree. I mean, it depends on k, but a single finite tree. And if you contain this tree as a subtree, then the Ehrenfreud value depends only on what's happening near the root. And that's the thing that we're going to use, that the locality is critical. So that's what I call the universal tree. All of this is for k arbitrary but fixed. All right, if we go back to the previous examples, these are what are called tree automata. So what are tree automata? They're sort of like finite state automata. It's not helpful if you don't know what finite state automata are, but okay. So there's a finite number of states. Some of them are accepted states and some of them aren't. And the key thing is that the state of a node is determined by these states of the children. With a further caveat that there's some number k, so that if you have more than k, let's say k is 10, it doesn't matter if you have 11 children in state red or 56 children in state red, it's going to be the same value. So there's a constant k that's given in the structure, so that when you count, when you get up to k, you just say there are lots of them. So in Israel, I think that's 9, right? I mean, if you have more than 9 children, you have omega children. So it's something like that. Okay, enough Israeli jokes. Okay. Maybe it's 12. I don't know. So notice that this fits the all 3 examples. We have a finite set of states. In 2 cases, it was green and red. In 1 case, it was green, red, and yellow. And in all of them, the state of the parent was determined by the number of children in each state, looking at the children and looking at their states. And so this has been studied. It's called a tree automata. Okay. And we call, so let me go back, and we call a statement recursive if we can create an interpretation of a tree automata that is giving a notion, setting some finite number of states, and giving an interpretation for each state in such a way that the root node is going to be an accepted state if and only if the property holds. So these 3 properties that I've spoken about are recursive states. There is an interpretation such that the root node is accepted. Under this interpretation, the root node being accepted is exactly the property that we wanted. So we're able to create a finite state automata. The interesting thing is that going backwards, there's an ambiguity. That what we'll see is that if you're given these rules for the tree automata, there will be different interpretations that also satisfy the same tree automata. In fact, let me give the key example there. Let me go back to the case of it being infinite, which is the simplest one. All right, the interpretation we wanted was that it was green if you had an infinite subtree, but there's another interpretation. It's always red. It's never green. Satisfies these rules. Satisfies these rules. So the tree automaton can have more than one interpretation. And the understanding of that other solution 0 is that the equation from Galton-Watson comes from the tree automata, but we have two different interpretations of the tree automata. One that never holds, and so that where it's never green, so that gives 0 as the solution, and one, which is the one we want, that the tree is infinite, and that gives the solution. So what's happening is the tree automata does not determine the interpretation. Okay, so let's go forward. And now the theorem is that if you have a first order statement A of quantifier depth K, then you can create the tree automata, and what you use is the Ehrenfreud value. So, all right, this again takes some things. If you look at for a given vertex, you only have a finite number of Ehrenfreud values. That's your state space. And for each vertex, the interpretation is you give the Ehrenfreud value of the tree rooted at that vertex. So you have a finite number of states, and one can show using the Ehrenfreud game or using some kind of methods of logic that that if you know the states of all the children with this proviso about counting, then you'll know the state of the whole tree. And that's something one can prove. I won't give the proof of that. So that shows that first order A are recursive, but it's not just first order A, it actually holds for monadic second order. So let me tell you what monadic second order is. There we allow us to use the word set, but we don't allow things like binary relations. So we can quantify over sets. So if we want to say that the tree is infinite, we just say there exists a set that contains the root, and for all x, if x is in the set, then there exists a y which is in the set, which is a child of x. And that'll mean that the tree is infinite. So we have these are the only two languages we're going to look at, first order language and monadic second order language. In both cases, by pretty much the same argument, you have tree automata. For a given k, you have the finite number of Ehrenfreud classes, and you get the tree automata. Okay, so let's look at the way we found the solution, and we can think of it as a fixed point. That is, we want to know the distribution on sigma, so let D be the set of distributions, which is a nice compact set, and we're looking for, so we make a map from distributions to distributions, and the map is as follows. Given a distribution on the states, take a single node, give it Poisson lambda children, give each of those nodes a state by this distribution. They induce the state of the parent, so that induces a distribution on the parent. That induces. So what we have here is a map from distributions to distributions, and what we're looking for is a fixed point. If we think of the three examples, that's what we did. We got these equations. Instead of writing them as two equations in two nodes, D is a two-dimensional space, so we just write it. We write it as a map psi, depending on the value lambda, of course, from D to D, and we're looking for solutions. And as we've seen, sometimes they're unique and sometimes they're not. And like I say, in this talk, that's what I really want to talk about. And here are the results. In the first order world, we have very good results. In the monadic second order, at the end, I'll make some comments. We're still puzzling over it. There's a lot of stuff we don't know. But in the first order world, it's a contraction. It's a contraction. This map from distributions to distributions. Remember, it's a compact set, distributions over a finite set. This map will be a contraction under the mapping psi. So let me go back. The mapping psi is... Oh, that's a very good question. We're going to do it for total variational distance, but if you take a high enough power, because it's finite dimensional, the metric won't matter. So instead of psi, there'll be some power of psi. That's going to be a very good point, yeah, which I'll actually, the arguments I'll use total L1 metric, but then by taking a high enough power, it's also true for L2. Yeah, no, very good question. Yeah. So our result will be actually, in fact, the actual result is some power of psi is contracting. So this is not technically correct the way I wrote it. Some power of psi is going to be contracting. So there it can be under any metric because you can just switch. And then from that, it follows that there's a unique fixed point. If you have a contracting map, there can only be one fixed point. And the thing that I really like about it is that the solution that you get is the solution of a system of equations. And the equations only have exponentials and polynomials. And they're all finite. You know, the probability of being 3 is lambda x cubed, e to the minus lambda x cubed over 3 factorial. And the probability of being omega is 1 minus the probability of all the numbers. By omega, I mean greater than or equal to k. So everything, all the functions involved are very simple. And so what happens is the solution, as the unique solution to this system, is a C infinity function. In fact, I think it's sometimes called an algebraic function. I'm not sure of the terminology, but it's a nice function. It's a really nice function. In particular, it doesn't look like those other two pictures. So if you look at the picture of being infinite, the thing is it's not differential, not differentiable. Even the actual picture, you're 0. In fact, this picture was in the Erich-Rainy. I can visualize it. It's in the Erich-Rainy paper of 1960. It's 0 until you get to lambda equals 1, and then it starts to grow. And at lambda equals 1, the function is not differentiable. In fact, it has right-hand derivative 2, which we saw in Baylor's talk. But here, if it's first order, we get a nice function. That's the result. And then the further results, when you condition on being infinite, then lots of nice things. And now it's a good time to mention that this is joint work with my student, who I'm sure you'll be hearing more about in the years to come, Mumanti Potter. And some of the results conditioning on infinite have already been submitted to publication. I think in the Zhirka volume, I think they were submitted there. And this one is what we're working on now is work in progress that we hope to submit shortly. Mumanti Potter, remember that name. Okay, so Don Knuth invented lots of great words, and this one never caught on, but I think for people in working on random things, I think it's a wonderful notation. You say something happens quite surely if the failure probability drops exponentially. I mean, of course, you have to have some variable that you're talking about, but it comes up quite a bit, and I'll tell you, I mean, if English is my native language, it sounds just right. It sounds just right. I mean, at least for American English. To say that something occurs quite surely, maybe I should say with an English, quite surely, it's quite surely occurs. And now, the definition, we say that let's look, we're determining the tree by this sequence of the number of children of the first node, the second node, the third node, using fictitious continuations, so maybe it actually stopped. And we say that a property, or a function, is rapidly determined if quite surely, looking at the first S, we have tautologically determined the truth of A, or the value of A if it's a function. Notice the two things are different. As an example, if we consider whether the tree is infinite, it's not rapidly determined. Because if you look, for lambda greater than 1, because if you look at the first S, if it died out, so you know tautologically it died out. But suppose that after the first S, we've got 50,000, well, it's looking pretty good, you know. I mean, but we don't tautologically know that it's going to be infinite. So that's a good example in the negative that being infinite is not rapidly determined. But once again, to be rapidly determined, we have to be quite sure that we are absolutely sure of the value of S. There's some close things to other things in computational complexity. I like this definition. It's my favorite definition.
That's for some value of S.
No, it's because the quite surely it means exponentially small in S. In S, yeah. So it means for each S, you look at the probability that you're tautologically determined. Probability that you're not tautologically determined is dropping exponentially in S. And the theorem is that the Ehrenfreud values are rapidly determined. Because if you look at the first S, you're going to get them. And basically the idea is if you look at the first S, well, this is a fixed tree, this Christmas tree. So the chance that you haven't seen this Christmas tree yet is exponentially small unless you died early. But if you died early, then everything's tautologically determined by the S. If you've died before you've seen XS, then it's tautologically determined. You might be true or false, I'm not saying which one, but you see the whole tree, so you know whether it's true or not. But if it hasn't died, then in the first S, with exponentially small failure probability, you've seen this fixed finite tree. And so now, and also you've seen what's near the root, and therefore you know the Ehrenfreud value. So,
which of the examples, so being infinite doesn't follow?
Doesn't follow.
What does? For example,
so the example I'm going to give is having exactly one child with one child. So you go along, and after the first S, well, you can't really look at all the S. You backtrack a little bit because some of them you don't yet know how many children and grandchildren they have. But if you back up a little so that you pretty much know, but then by time S, the chance that none of them would have had one child or which had exactly one child would be exponentially small unless things stopped early. But if they stopped early, then you knew. And so that's the example. And that's really this example as well. I mean, it generalizes. So, I mean, in fact, I do it with martingales because, we have this book, we have this whole chapter on martingales. So, but there are other ways to prove it. Okay. So now you can get a unique fixed point. So you look at this map psi, but you take it to the S power. So it means you take a node, you generate the first S generations by the Poisson tree. Now you look at generation S. Of course, maybe there's nothing there, but you look at generation S. You give each of them independently a state by the distribution, and then you induce up to the top, and you get a state for the root. So it's just psi iterated, and that's psi to the S of X. And so when sigma is quite surely determined, then when you look at psi sub S of X, but by the time you've gotten to the S generation, well, quite surely determined is actually just from the first S nodes, but then that implies if you've seen the first S generations, quite surely, so with failure probability e to the minus s, you actually know it. So that means you already know what the Ehrenfreud value is going to be. So it doesn't matter what states you give to the things below. The state on top has already been determined. So so that when that's true, psi sub s of x, it doesn't matter what x is, except for exponentially small probability. And that means that the limit, as s goes to infinity, the exponential failure rate is going to 0. That's actually all we really need. And so the limit point is independent of x. So that means that psi sub s has a unique fixed point, because after all, psi sub s had two unique fixed points, x and y. Then you just you run them both, and they wouldn't be converging to the same point. So we get a unique fixed point. What I further want to say, but let me see the time. So I have 45 minutes, and I started at 9:30 plus epsilon or so. So let me say 9:35. Okay, so let me skip the proof of contraction, which is a nice proof, because I want to move on to, it's looking like, okay. So I want to talk at the end about monadic second order, where things are still quite mysterious to me. So monadic second order, like I said, you quantify over sets of vertices. And existential monadic second order is where you just have the quantification over sets is pushed to the left. Maybe in Hebrew it's pushed to, no, you still use the math, right? I mean, it's still pushed to the left. And it's all existential, so that's a sub part of it. So when you have a tree automata, you can create a monadic second order statement. Namely, you can say that every point is either, so you have three sets, red, yellow, and green, okay? And the statement is that for all x is either red or yellow or green. And then the statement is that for all x, if x has 2 green children and 1 yellow child and 5 red children, then it's green. And you just make this finite list of statements, and you get a monadic. So if you have a tree automata, you get a monadic second order, but you can do it in several ways. Okay. So when you have a tree automata, you get an equation in a definite way, and the equation has a solution, because we're looking at the probability of being accepted, so we add all the accepted states. But as we've seen, it's not always unique. And one of the things that we're still open on, we'd like to characterize the times when we get a unique solution. We know that first order statements, we do get a unique solution, and we have a lot of cases where we don't. Okay. So, but here's a nice theorem. Suppose we have given the tree automata, we create the existential monadic second order statement, which is that there exist sets, red, yellow, and green, that have the nice properties. Then the claim is that when we solve the equations and take a solution A, that we can actually realize that that's a lower bound on the probability of A holding. And the reason is we look at the nth generation, and if we put on the nth, we look at the random tree, we have a double randomness. We look at the random tree down to the nth generation. On the nth generation, we put this fixed point vector, capital X, that induces capital X up on the root, because it's a fixed point of psi. And therefore, that will say that in this double randomness, the probability of being accepted would be A. But that means that, we don't really need the epsilon here. That means that the probability that there is a way to accept the random tree is at least A, because in the double probability it's A. So the probability that there is something to put on the nth generation so that you do accept is at least A. And then you say, okay, that means that this probability will be at least A for infinitely many n in our space. And in the end, you use compactness. You use compactness because if you take your tree, this is just putting states down at level n and working your way. But if for an infinite number of n, you can place states on level n so that when you work up, you're accepting the root. If you can do that for infinitely many n, you can, by compactness, you can do it for the whole tree. You can do it for the whole tree. Inverse limit, or however you want to say. So we do get this lower bound. One of the things that comes in that's handy is non-determinism, where we take a tree automaton and we allow the nodes to have more than one state, that is the set, and this represents the set of possible states they can have. So you have the tree automata, you look at a node, what are the possible states it can have under any interpretation? And so again, though that's a finite number, it's a non-empty set. So in the example that I have here, let's say that something is green if it has exactly one green. But now you turn it non-deterministically, you call the states green, red, or green, red. And then it's green, red if it has at least one green or green, red. Okay, and what happens is in the non-deterministic situation, you can see that if you take the tree automata A and you make the existential monadic second order statement non-deterministic A, which is that there exists a choice of a set of states to each node. So this is similar to non-deterministic finite state automata. The new states are the subsets of the states, and you actually get the maximum fixed point. So we do know it in some cases, but I can see my time is running out. I'll skip the example. Okay, this is what I mentioned before. Here's the other way of saying what I've been working around. I mean, if you're given a tree automata, often there will be more than one interpretation. Indeed, let's look at the case of having exactly one child that has exactly one child. I've given you one interpretation. There's actually another interpretation, which is you're green if in your tree you have a node with exactly one child that has exactly one child. But also, if you're infinite, if your tree is infinite, I'm going to make you green anyway. I'm going to make you green anyway. And that still satisfies the tree automata. It's still, if you have a green child, you're green. So it's a second interpretation, but the interpretations only differ on probability 0. If you're infinite, see, it's an easy exercise. Well, if you read the right book, it's an easy exercise that if conditioning on the tree being infinite, there's going to be a node that has exactly one child that has exactly one child. So while tautologically there are two different interpretations, the interpretation is determined up to probability 0. So to my mind, the structural question is not when is it tautologically determined, but when is it determined up to probability 0. And that to me is an interesting question. Here's a more general question. What happens with arbitrary MSOs? Answer, I don't know. And let me finish with one of my favorite authors, as the Czechs might appreciate, Kundera, and who always says wise things about both life and mathematics. So, well, you know, it's a great joy to do mathematics. It's a wonderful, great joy. And it's a particular great joy to do mathematics with Noga alone. So happy birthday, Noga.